Hello, my name is Gretchen T. Lapidus, and I work in the Departamento de Ingeniería de Procesos e Hidráulica en la Universidad Autónoma Metropolitana, Unidad Iztapalapa, in Mexico City. And my seminar today is titled Minimizando the Hydro in Hydrometallurgy. It was presented at Hydrometallurgy 2018 in Ottawa, Canada. Many of us have overheard conversations in several different places where people commented that hydrometallurgical processes employ toxic chemicals, cyanide, ammonia, ferrochloride, etc. Hydrometallurgical processes use strong acids and bases. Acetic acid, nitric acid, hydrochloric acid, sulfuric acid, and sodium hydroxide. Hydrometallurgical processes employ large quantities of reagents that require downstream waste treatment. And overall, hydrometallurgical processes use and pollute a lot of water. Well, they're absolutely right. Today's hydrometallurgical processes usually have these faults. Many people use arguments in favor of pyrometallurgy because it's fast and easy. And for the most part, iron stays in the slag. Yes, this is true, but today's minerals are more complex. We worry more about greenhouse gases and our carbon footprint, and not all applications are on a large scale. And most of all, hydrometallurgy is changing. For pyrometallurgy, flotation separation is essential. However, as can be seen in the images below, there are many minerals that, or mineral ores that are very complex. As we can see, according to the scale in each of the images, it's almost impossible to separate the different mineral phases from each other just through flotation, grinding and flotation. It's much too small, and the phases are associated much too closely. Additionally, there are many mineral phases that are complex of themselves and which contain various metals, such as the ones of lead, bismuth, antimony, and silver in sulfide minerals that occur as alloys. We can call them alloys. Also, how much water is needed for flotation separation? The math is easy. The cubic meters of water necessary or used in the flotation are the amount of tons of extracted ore multiplied by 2. For example, in Peñasquita, in Mazapil, Zacatecas, in Mexico, 130,000 tons per day are processed, which is around 260,000 cubic meters of water per day. In the Saltillo district, where these are very close to this area, there are 800,000 inhabitants, and they use 85,000 cubic meters per day of water. So as you can see, the mining operation uses several times more water than the surrounding population. So pyrometallurgy is not completely innocent. Where does all the water go after use? Well, we have quite a bit of water loss by evaporation, retention in tailings or residues, about 55% solids and 45% liquids, infiltration. How can we decrease water consumption? In many parts of the world, the problem has been lessened, encouraged by environmental legislation or by necessity. For example, in Arizona, in the older operations, there's an average of half a cubic meter of water per kilogram of copper. In the newer operations, there's less than 10% of the water used per kilogram of copper recovered. Still, improvement is necessary. But enough of pyrometallurgy. Let's talk about hydrometallurgy. Hydrometallurgy, or as Shakespeare once said, what's in a name? The challenges that we must address are the following. Use less fresh or potable water. Should not pollute air, water, or soil. It has to compete economically with pyrometallurgy, and we must live in harmony with the neighboring communities. In hydrometallurgy, we have to follow the 3 R's: solution reuse, recycle, or recovery. Reuse is after the metal is removed at a similar pH, reagent concentration, and impurity levels. Recycle, when purification is necessary before reusing. And recovery, salvage the water and the reagents. Reagent minimization, selectivity in leaching and recovery of metal values. Employ clean oxidants and reductants such as peroxide, ozone, and hydrazine, among others. Use of electricity when possible instead of chemical oxidants and reductants. Integral process conceptualization. This is try to conceive the entire process and not only one unit operation, not only leaching or solvent extraction, the entire process. And map out the trajectory of all the chemical species, especially water. At this point, we will give some process proposals. Some are viable, and some are frankly crazy. We're going to see the use of clean oxidants and reducing agents, solution recovery, and electricity used as oxidants or reducing agents instead of chemicals. We'll start with employing clean oxidants and reductants. Our first example is the obtention of lead metal from lead that's contained in galena concentrates or in used acid batteries by selective leaching at room temperature and pH 7 using sodium citrate solutions. The first four reactions that we see here are actually the reactions that take place when we're leaching a used lead acid battery. So we have lead metal or lead alloy, we have lead sulfate, lead oxide, and lead dioxide. And as an oxidant, we'll use peroxide, and as a reducing agent, we'll use hydrazine hydrate. And the soluble complex that's produced in all four cases is lead citrate, which is soluble at pH 7. In the case of galena concentrates, and this is a very selective reaction, we have galena reacts with peroxide, hydrogen peroxide, to form also lead citrate, soluble. Once we have our leaching done, then the pregnant solution is sent to electrolysis, where we have a very selective electrolytic process, very efficient, which combines electricity to form lead metal, and in the case of the anode, we form oxygen from water. We can combine the two major stages in the process, the leaching and the electrolysis, into a flow diagram. After leaching, the inert or the non-reacting phases are filtered out. In the case of the concentrate, this would contain other sulfides and non-sulfide phases. In the case of the galena concentrates, we can anticipate that a small amount of silver or copper could be leached, and these can be cemented by the addition of lead metal and filtered out as metal, as copper and silver metal. And the pregnant solution is then sent to electrolysis as we had anticipated. After electrolysis, the lean solution is, which contains sulfate in both cases, sulfate ions, which have to be removed before we recycle the solution. So we can take a purge and treat the solution and do a makeup of with citrate and water, and recycle that all back to the leaching. The characteristics of this process are it's citrate based, which is citrate is a natural buffer. So if the reactions need hydrogen or produce hydrogen, such as in electrolysis, the pH stays basically the same. It's at ambient temperature, pH 6 and 7, very selective for lead. In concentrates, we have other sulfides which at these conditions do not react or react very, very little. And also in the lead batteries, as the alloying metal, sometimes they have antimony, sometimes they have tin can come in there. And we find that these are not leached in the citrate solution at these conditions. It uses clean oxidants and reagents, reducing reagents. And what are the challenges? Well, the sulfate removal is a challenge, and the treatment of the purge solution should be very small. The amount of purge, and how we treat that and remove the sulfate to recover the citrate and the water, that is a challenge. And the temperature, operating temperature, cannot be more than 40 degrees, because that's at that temperature the citrate becomes decomposes. The next process is chalcopyrite leaching, but this is with a reductive pretreatment. In an electrolytic cell at the cathode, chalcopyrite comes into contact and is reduced to chalcocite in the first reaction, liberating ferrous ion and hydrogen sulfide. And at the same electrode, the chalcocite is further reduced to copper metal, and more hydrogen sulfide is released. And of course, we have the parasite reaction, which should be minimized, which is the production of hydrogen. At the anode, we have the hydrogen sulfide being converted to sulfur in an oxidation reaction. The solid is then passed to an oxidation stage where the chalcocite and the copper metal are leached or oxidized with cupric ion in the presence of acetylnitrile. The presence of acetylnitrile allows the copper to be reduced from copper 2 to copper 1 to cuprous ion, and we have the formation of sulfur and the soluble acetylnitride with the cuprous ion. This solution is then sent to an electrolysis where the copper, the cuprous acetylnitride ions are reduced to copper metal in the cathode and liberating the acetylnitrile, and at the anode, the same molecule, the cuprous acetylnitrile molecule or complex, is oxidized to copper 2, which regenerates the oxidant. And of the solution from the electro-assisted reduction, we have the formation of a ferrous ion, which in a later stage is reduced to iron, metallic iron. The results under the best conditions in the square prototype with 50 grams of copper concentrate per liter. As you can see on the left, we have the reduction reaction, which produces ferrous ion. And as you can see, with time, the ferrous ion is being released into the solution. And if we take it by the hours, each hour of reduction, if it is only in contact for 1 hour, we have in the next stage, which is the oxidation with the cupric ion in the presence of acetonitrile, we have a very small amount of copper released into the solution. But as the reduction time is increased up to 7 hours, so we now have was practically 100% of the copper being leached in the oxidation phase. And as you can see, at the very beginning, the initial 10 minutes or 5 minutes, you can see that there's very, very large amount of instantaneous dissolution. This is actually from the copper that's reduced all the way down to the copper metal, and the rest of the remaining copper is leached a little bit more slowly, is actually from the chalcocite. The reduction time definitely influences the copper extraction, and we can maximize, if we can maximize the contact between the particle and the cathode in the reduction stage, this optimizes the process. The chalcopyrite leaching process with a reductive pretreatment begins with the feeding of the copper concentrate to the reductive leaching or pretreatment phase, where the ferrous ion is liberated and the solution, the pregnant reducing solution, is sent to the to iron electrolysis. The solid, which is now reduced to chalcocite and copper metal, is sent to the oxidative leaching stage, where the clean oxidant, the cupric ion in presence of acetonitrile, oxidizes the copper to cuprous ion. The pregnant solution is then sent to copper electrolysis. The characteristics of this process are ambient temperature, pH near 1.8. It's very selective for chalcopyrite or chalcocite. And the interesting part here is the oxidative leaching stage uses the redox pair of the cupric ion and cuprous acetonitrile complex. The challenges are, for this process, that there's quite a low current efficiency, especially when we have poor particle cathode contact. Here the challenge is to find a reactor design which optimizes the particle cathode contact. And the ferrous ion electrolysis to iron metal is still not investigated sufficiently. In our group, we have also investigated chalcopyrite leaching via the oxidative route using hydrogen peroxide as the clean oxidant. In this case, we form cupric ion, ferrous ion, and elemental sulfur, which in the presence of excess hydrogen peroxide forms sulfuric acid. We would like to minimize this second reaction. We can remove the ferrous ion with solvent extraction and electrowin the copper as usual. Like a very conventional diagram. However, in this case, we would like to reduce the hydrogen peroxide consumption. And this is done by including in the aqueous solution ethylene glycol, or other polar organic solvents have been used. And in this case, we can reduce the amount of hydrogen peroxide consumption. The characteristics are ambient temperature, pH between 2 and 3. This is very important for the selectivity of the process for chalcopyrite or chalcocite. And the challenges are, as usual, the iron removal and, of course, the efficient use of hydrogen peroxide. Next process that we're introducing is the platinum group metal leaching. And for this particular leach, we need very high potential. So we use ozone in a chloride medium, and this chloride medium is basically salt, sodium chloride, which allows us to use a pH of around 4. The next part of the process would be the cementation reactions, which are very efficient with zinc powder. So the process that we have devised for this is for these magnetite concentrates are leaching with ozone at pH 4 with a high concentration of chloride ion in the form of sodium chloride, and then the solid residue is filtered out, and the pregnant solution is then cemented with zinc powder. Out of this we get platinum metal, palladium metal, and also gold is also leached and cemented in this case, and we can recycle the salt solution back to the leaching. The characteristics: ambient temperature, pH 4, chloride chemistry. So here in the cementation, we don't have a problem with chloride. The challenges are base metals must be previously removed, except for iron, because the iron goes to hematite, which is a solid. It stays in the residue. And the scale up right now is uncertain. All of the previous processes had to do with using clean oxidants or reducing agents, and now we'll deal with processes that have to do with solution recovery. First off, we'll describe acantite and gold leaching with ammonium cupric thiosulfate. And in this case, we'll be leaching the gold by oxidation, and the silver will be an exchange of the copper for the silver to form chalcocite in the solid. So once we have the pregnant leaching solution, it will be cemented with copper metal, and we'll get the gold and the silver metal. And then with sufficient aeration, the the cuprous thiosulfate can be oxidized back to cupric ion to be recycled back to the leach. For this case, the processing scheme is more complicated because of the complexity of the leaching solution itself. We have the cupric ion, we have the ammonium or ammonia, we have thiosulfate ion, and in large concentrations, and we absolutely have to be very conservative with these reagents because they're in very high concentration. And so we have to have a lot of rinsing in the process. And to complete the water balance, we have to have some way of recovering the water in excess water that we have in this processing, which we're proposing that we use reverse osmosis. And so the characteristics are ambient temperature, pH 9 to 10, and this is really for high-grade copper ores because this copper in itself is the oxidant in the process. The challenges are it's complicated chemistry. I said we have to keep a very strict control on the cuprous balance and the copper recovery from the residue that, remember, especially for the silver exchange, we have copper in the we have chalcocite in the residue. So we have to have some kind of a further process to recover that copper. The last two processes have to do with the use of electricity instead of chemical reagents. We had a little taste of that with the chalcopyrite pretreatment, reductive pretreatment, but in this case, it's almost completely substituting chemical reagents for electricity as oxidants or reducing agents. This first process deals with using electro-oxidized thiourea to leach gold and silver. The thiourea, if it's electro-oxidized under controlled conditions, forms formaldehyde disulfide, which is the dimer. And this dimer actually becomes the leaching agent for the sulfur in the acanthite or for the gold metal. And under very controlled conditions, we get the leaching of silver as silver, the thiourea complex, and also the gold thiourea complex. Once we have the pregnant solution, this goes to direct electro recovery in the cathode, where we form silver and gold metal. Electro-oxidized thiourea process begins with the thiourea solution, which is partially oxidized under very controlled conditions, to the dimer. And this solution is fed along with the precious metal concentrate to the leaching reactor. The product is then sent to filter out the leach residue, and the pregnant solution is sent to the cathodic compartment of the electrochemical reactor where the gold and silver are reduced to their metallic form. And this slurry is sent to a filter to recover the gold and silver in metallic form as doré, and the barren solution is sent back to be recycled to the anodic compartment. The characteristics of this process are ambient temperature. The oxidant is actually electricity and the reducing agent also in the electrochemical reactor. It has very low energy requirements, and the product of the process is gold, silver, doré. The challenges for this process are it's not adequate for acid-consuming ores. That's why we use concentrates for this process. And also, base metals can decrease the yield, especially if there's a large amount of soluble copper. However, we can correct this problem by additives that depress the leaching of copper, especially. The last process scheme that I would like to describe is manganese dioxide production from low-grade ores, or it could be batteries or other e-wastes. It begins with the leaching of manganese dioxide with the ferrous ion, which is a reductive leach, and we reduce the manganese from manganese 4 to manganese 2, which is soluble in sulfuric acid. This process also produces ferric ion. However, in the reaction is meant to take place in electrochemical reactor, where on the cathodic side, we're continuously regenerating the reducing agent. We have as a product of the leach ferric ion, but in the reactor, it's converted back to ferrous ion. And this ferric-ferrous pair act as an electron carrier to and from the manganese particle. We can use only a small amount of ferric ion, ferrous ion, since this is going back and forth in the cathodic compartment of the reactor. And on the anodic side, the manganese is oxidized to manganese dioxide, and we recover the acid at the same time. The manganese processing scheme initiates with the feed of mineral or e-waste containing manganese in solid form is mixed with sulfuric acid, which has been recycled, and goes into the cathode compartment where the manganese dioxide is reduced to soluble manganese. The slurry is then filtered to remove the inert solids, and the pregnant solution is sent to the anode compartment, which oxidizes the soluble manganese back to manganese dioxide, and the slurry is sent to filtration, where we recover manganese dioxide and the sulfuric acid solution with the ferric ion is recycled. If there are impurities, a purge is taken and makeup of sulfuric acid and recycle back to the beginning. The characteristics of this process is ambient temperature, 1 molar sulfuric acid. This is an electro-assisted reductive leaching, which uses a small amount of ferrous and ion, which goes back and forth between ferrous and ferric. The challenges, can we scale it up? We don't know. We've done it in the laboratory. So finally, we've come to the conclusions of all of these proposed processes. And we can say in general, mineral processing and metallurgical process require a large amount of water. Unfortunately, this will not change. However, the use of fresh water can be decreased if solutions can be reused, recycled, or recovered within the process itself, the 3 R's. This also minimizes reagent requirements and waste generation. And finally, integral process design and detailed material balances are of utmost importance in all hydrometallurgical processes. And we thank you very much. Muchas gracias.